So we've been analyzing primitive Pythagorean triples, which recall satisfy the Pythagorean theorem a squared plus b squared equals c squared, where a, b, and c all have to be integers and have no common factors. That's the difference between a primitive and just a regular Pythagorean triple. A primitive Pythagorean triple cannot have any common factors between a, b, and c. Now, we learned in the last video that there are infinitely many of them, and we'll actually see why there are infinitely many primitive Pythagorean triples. That it was kind of like this obvious little tidbit that we could generate more just by having one of them. We've learned also that A is odd, B is even, and C is odd. Now, A and B could switch. A could be even and B could be odd, but it makes no difference because you're adding them. And A and B are just names that we give them. Okay, so now the question is, we would like a formula to calculate primitive Pythagorean triples, right? Because we can explore them, we can make some observations about them, but how do we come up with them other than by running computer simulations? Now, just as a key point here, all primitive Pythagorean triples are Pythagorean triples. Therefore, by focusing on these primitive ones, we're only addressing how to compute a specific subset of all of Pythagorean triples. Remember, not all Pythagorean triples like 8, 6, 8, is that what I'm thinking? 6, 8, 10 is one Pythagorean triple, but it's not a primitive Pythagorean triple because 6, 8, and 10 have a common factor of 2. So we're going to develop a formula that allows us to compute primitive Pythagorean triples, which is just a subset of all the triples there are. Okay, now one thing that we're going to do in order to calculate these is if we write a squared plus b squared equals c squared, and then we actually subtract over the b squared, we get c squared minus b squared, which would be, a squared equals that. Well, the cool thing about the difference of squares is that it actually factors into c plus b times c minus b, or it doesn't matter what, c minus b first. C minus b times c plus b. Okay, so if you FOIL this out, you get c squared there, then you'll get plus bc minus bc. Those cancel each other out, give you 0. Negative b times positive b gives you b squared, and so as a result, that simplifies down to c squared minus b squared. So what that allows us to say is that a squared, the square of this integer, is the same thing as c minus b times c plus b. Okay, so it can be, in other words, factored into c minus b, c take away b times c add b. Then we can make some observations about the relationship between b and c by using some of our pairs. So what kind of observation, what kind of hypothesis can we make about c minus b and c plus b? So let's take a look at certain values of a, b, and c. We know 3, 4, 5 is a primitive Pythagorean triple. Then let's build a column for c minus b and another column for c plus b. We already know that if you multiply c minus b times c plus b, then you're going to get a square root. Okay, so c minus b, 5 minus 4 is 1. 5 plus 4 is 9. 1 times 9 gives you 9, and 3 squared is also 9. Okay, so I'll just put a squared over here for reference. So you see 1 times 9 gives you 9. Nice. Okay, what was another one we found? Another primitive Pythagorean triple that we have is 5, 12, 13. Let's look at 5, 12, 13. 5, 12, 13. So 13 minus 12 is 1. 13 plus 12 is 25. And then 5 squared is 25. So 1 times 25 gives us 25. Let's pick now 15 8, and 17. By the way, a key observation here that's going to become important is that, remember we said A is odd and B is even? That's going to be the key here, is making sure that we identify A and B correctly. Otherwise, if we switch A and B, this is going to become a little bit more interesting. So let's always make sure that B is even, as we've indicated. Okay, well, if that's the case, then C minus B is 17 minus 8, which is 9, and 17 plus 8 is 25. 9 times 25 is 225, and 15 squared is 225. So this works out as well. Now we can keep on doing this, but one thing that I want you to notice is that C minus B and C plus B are themselves perfect squares, at least in these examples here. So notice that 1 is the same thing as 1 squared. 9 is 3 squared. 1 is 1 squared. 25 is 5 squared. 9 is 3 squared. 25 is 5 squared. So it appears as an observation that C minus B and C plus B are perfect squares, meaning that you can write them as the square of an integer. That's pretty cool. So how do we know that this is always true? Well, there's a couple of things that would be helpful in knowing that. And then once we're able to establish this with certainty, then we can actually construct formulas for how to calculate B and C. So bear with me for a moment here. Let's think together. First off, if we restrict ourselves to the case where A, B are all non-zero integers, then it follows that C minus B will be different than C plus B. Okay, so that's got to make sense, right? Because if they're non-zero, then C minus B, if you take away B from C, then that's going to be smaller than C plus B. Right? So C minus B has to be less than C plus B. Has to be, right? So if C minus B times C plus B is A squared, this suggests that the product C minus B times C plus B gives us a perfect square, right? Because this right-hand side is a perfect square. So if this is 36, then C minus B times C plus B has to itself be a perfect square because it has to equal 36. So if you take the square root of both sides, another way of thinking about this, then you've got to be able to get an integer when you take the square root of C minus B times C plus B. So what do we know about the individual factors C minus B and C plus B? Well, we want to establish they are themselves perfect squares. And one way to do this is that, first of all, we know that they can't have any common factors. Not having common factors would mean that the greatest common divisor of C minus B and C plus B would therefore be 1. That's the only number that would divide both of those quantities. Now let's lay this out for a second. I'm going to make this argument. I'm going to say that let's suppose that D is the GCD of C minus B and C plus B. Okay, so in other words, D is a number that just divides both of them. What we want to establish is that the only number, D, that will work, that in other words, D is equal to 1. So show that D is equal to 1. That is the greatest common divisor. So here's how we can go about this. So first of all, if I were to add C minus B and C plus B together, since they both have a common factor of D, I could factor out a D from both of these terms, right? So in other words, that if C minus B and C plus B are both divisible by D, then so is their sum. So C minus B plus C plus B is going to give us just 2C. Also, if we take the difference between C minus B and C plus B, that is also divisible by D, because we can factor out a D from both of those. And in this case, we would get negative 2B. Well, let's subtract them in the opposite order. So In this case, c minus c is 0, b minus negative b will give us 2b. Okay, so that means that since this means that d divides 2c and d divides 2b, right? Because the two sides are equal. We know that d divides the left side, so it's got to divide the right side if they're equal. And if d divides the left side, it's got to divide the right side since the two sides are equal. So what do I want to know now? Well, I want to know that d is equal to 1. Okay, well, what do we know? We know that b and c have no common factors, right? I'm not making the argument yet for c minus b and c plus b, but b and c have no common factors because a, b, c, that triple, is a primitive Pythagorean triple, right? So by construction, this is why we're focusing just on primitive, but if it is a primitive Pythagorean triple, then there's no common factor between a, b, and c. Therefore, if d divides both 2 times c and d divides 2 times b, and c and b have no common factors, well, that means that d would either have to be 2 or 1. Right? D could be 2 because 2c divided by 2 is equal to c, which is an integer. And if d was 2, then 2b divided by 2 would be b, which is an integer. Or d could be 1, right? That's the only two numbers that d could be in order to divide that, and b and c to have no common factors. So d equals 1 or 2. Okay, well, what else do we know? We also know that c is odd. C is odd, and b is, what do we say about b? We said b is even. B is even. Okay, well, if c is odd, then c cannot be divisible by 2, but that doesn't necessarily allow us to eliminate d equals 2, because remember, d is dividing 2 times c and it's dividing 2 times b, so a d of 2 would work in either case. However, let's go back to the product. C minus b times c plus b. Okay, well, that we know is c minus, we have an odd minus an even, and an odd minus an even is an odd number, and c plus b is an even plus an odd, which is an odd number. That equals a squared. We already know a is odd. So my point here is that in order for d to divide c minus b and to be able to divide c plus b, if c minus b is odd and c plus b is odd, then d being equal to 2 cannot possibly divide an odd number. So since d can't divide an odd number and be equal to 2, that means d is equal to 1. That's our only possibility there. Okay, now from there, we know that the GCD between c minus b and c plus b is equal to 1. We know that c minus b times c plus b gives us a perfect square. What we can also infer from this is that c minus b and c plus b are both perfect squares. This is the only way for that to happen. Now, we're not going to get into the theory of why that is, but by having only a divisor of 1 and for their product to be a perfect square, the only way for this to happen, let me point this out, if we take the square root of both sides, it's equal to the square root of c minus b times the square root of c plus b. And for that c minus b, for this product to be an integer, c minus b itself would have to be a perfect square, so that the square root of c minus b is a perfect square, and the square root of c plus b is also a perfect square. So if that's the case, if c minus b and c plus b are both perfect squares, that means that c plus b is some integer squared, and c minus b is some other integer squared, different integer squared. And that's the key that's going to allow us to solve for b and c. So let's solve for b and c. We have b is equal to s squared minus c. If I take this first equation and solve for b. Now let me use substitution in the second equation. In the second equation, I'll substitute in c minus b. Okay, well, b is equal to s squared minus c equals t squared. And this is going to give me the equation 2c minus s squared equals t squared. So solve for c. We get c is equal to t squared plus s squared over 2. So there's our value of how c should be computed given two integers t and s. B is going to equal s squared minus c. Well, now we know that c is equal to t squared plus s squared over 2. And we're almost there. To get a common denominator, let's make this 2s squared over 2 minus t squared plus s squared over 2. Now, since we're subtracting, don't forget to distribute that minus sign, we get 2s squared minus s squared is s squared minus t squared over 2. So this is how we would get a value for b. So what we've just come up with is how to calculate b and c, knowing that c minus b times c plus b is going to be a perfect square. So the question is, how do we use these formulas, right? Well, to use these formulas, we would first need to pick a value for s or t. Because remember, s and t are just some integers. So let's just pick, for demonstration purposes, let's just pick t is equal to 1. If t is equal to 1, then just for that value of t, we could calculate a, b, and c. So for t equals 1, we get b is equal to s squared minus 1 over 2. C is equal to s squared plus 1 over 2. And a is going to be the product of c minus b and c plus b. So how do I begin picking values here? Well, in order for me to pick values for this, I have to find a value of s that will make the numerator divisible by 2. So that means in order for this to be divisible by 2, I'd have to have an odd number for s. Okay, so let's actually, let's do this. Let's make another table. B and C in here. And we'll start off with different values of s that will make this work out. So again, s has to be an odd number so that I get an odd minus an odd is divisible by 2. So let's pick 5. Let's pick 3 for s. So that means 3 squared is 9. 9 minus 1 is 8. 8 divided by 2 is 4. Now I'll have 9 plus 1, which is 10 divided by 2, which is 5. So if b is 4, c is 5, then a is going to equal the square root of c minus b times c plus b. Okay, well, c minus b is 5 minus 1 is 1. C plus b is 9, and the square root of 9 is equal to 3. So now the triple that we've just generated is the one that we know and love, 3, 4, 5. Again, I can pick a different value for s. The value of s is not itself important other than helping us generate the ABC. So let's just pick another one. Let's pick 11. Okay, if s is 11, 11 squared is 121. 121 minus 1 divided by 2 is 60. Notice that b is even. Here we get s squared, which is 121 plus 1 is 122. 122 divided by 2 is 61. And then a is going to equal the square root of c minus b, which is 1, times 60 plus 61, which is 121, which is equal to 11. So now I've generated the primitive prime triple 11, 60, and 61. And you can verify that that actually works out. That's just for t is equal to 1. S could be any odd number, so we could do this for 5 and 7. We could even do it for 1's not going to be an interesting one, because if we pick 1, then we get a b value of 0. We don't really want that, but any value of s will work. Then we can change the value of t to be another integer, and again, pick the corresponding value of s. And now we have a way of just generating as many of these primitive Pythagorean triples as we want. So here's my argument for why there are infinitely many primitive Pythagorean triples. Well, just for t equals 1, s could be any integer, any odd integer. So how many odd integers are there? Well, there's infinitely many of them. And so if there's infinitely many odd integers, there's infinitely many choices for s, given just the specific value of t equal to 1. And so I could generate these all day long. And so now we have a way of understanding primitive Pythagorean triples and generating them. The question that we might still have is, well, how do we generate Pythagorean triples? What if we don't necessarily want to be limited to just primitives? Well, that's for another video.